Hi, this is Professor Fernandez doing class notes D in lesson 5. So in this class notes, we are asked to find the general solution of this CC solved, and this is going to end up having complex roots for the characteristic equation. So I just wanted to scroll up here and remind you of the main takeaway that when you have a complex solution to the characteristic equation of a CC solved, then by being able to pick out the real and imaginary parts, you can write out the corresponding real valued solutions to the ODE. And these are fundamental solutions, as I say here. This is something that you will check in one of the practice problems. All right, so let's take all of that for a test drive in this example and see how it all works out. So find the general solution of this. So we're going to write out the characteristic equation first. R squared plus 2r plus 5 equals 0. And then we are going to try to solve this. It doesn't factor easily because you get complex roots. So we'll apply the quadratic formula here. Negative b plus or minus the square root of b squared minus 4a and c all over 2a. And then we just do a little bit of the arithmetic. Under the square root, we get 2 squared is 4 minus 20 all over 2. And that leaves us with a square root of negative 16 over 2. And we can split that up. Square root of negative 1 times square root of 16 divided by 2. So we get minus 2 plus or minus square root of 16 is 4. Square root of negative 1 is I. There we go. And then we can get rid of a factor of 2 to leave us with negative 1 plus or minus 2i. So we get two roots, as we should, because we're solving a quadratic equation. However, as I mentioned in this remark up here, we are only ever going to use the positive imaginary roots to write out the general solution. We're not going to use the negative imaginary root because all that does is, in the end, give you the same general solution. Okay, so we're going to completely discard here the negative 1 minus 2i, and we won't write out the general solution for that case. It'll just duplicate what we get for the positive imaginary part 1. So we're going to write out the solution for this complex root. Alpha here, this is our real part. This is our imaginary part. So this leads to two real value solutions, e to the alpha t cosine beta t. And then number 2, y2 of t, e to the alpha t sine beta t. Okay. And again, if you're wondering how did the sines and cosines come up, right? That was this portion of the derivation where we used Euler's formula to make sense of this complex root e to the rt and decompose it, right? And that gave us something that had the form u of t plus I v of t, and that kicked in the theorem that we, the theorem that we discussed in the previous video, right? So it's from there that we extracted the u and v solutions, which led us then to what we're using now, this form for the fundamental solutions to the CC solved in the complex case. Okay, so to return down here, we have our two solutions, y1 and y2, and they're fundamental solutions. So from here, we just take the linear combination, and they give us the general solution. They both have e to the minus t, so actually let me factor that out, save myself a tiny bit of writing, and then we're left with c1 cosine of 2t plus c2 sine of 2t. Okay, and that is my general solution.